This is lecture 4 of Logika računalništvu, logic in computer science. And today we're going to look at having explored propositional logic very thoroughly over the last 3 weeks. Today we're going to begin looking at a more expressive logic. That's the logic known as predicate logic, or also known as, so it's also very common to call it, so also known as, aka, first order logic. So in the lectures I shall use predicate logic and first order logic interchangeably, both mean the same thing. The textbook by Michael Huth and Mark Ryan calls the logic predicate logic. Now, predicate logic is more expressive than propositional logic, so that's useful in situations that we want to say express properties that cannot simply be stated as finite combinations of, well, as a single Boolean formula basically, or finite conjunction of clauses, as we've been seeing recently when we look at conjunctive normal form. As with propositional logic, we're going to follow roughly the same order, in that we're going to start with how to reason with predicate logic, and once again we're going to use natural deduction for reasoning in the most natural way, in a formal way. That's a very precise mathematical way, but still using a natural style of reasoning. And then in the subsequent lectures we're going to move to more algorithmic properties of predicate logic, ending once again with applications. Okay, so we're going to have a more expressive logic than propositional logic. So that means extending the language of propositional logic with some extra constructs, linguistic constructs that give the additional expressivity. I want to motivate that by looking at two possible examples for things we might want to say. The first one is going to be taken from computer science, because this is logic in computer science. So imagine we want to describe properties of a network of devices, and we don't know how many devices are connected into the network, so we don't just simply have a finite list of names for all the devices. We want to be able to express generic properties that will hold of the network, however many devices we have connected. And moreover, we're going to deal with a particular kind of network, which is called the server-client model in computer science. So devices are either servers, those are devices that provide some sort of service, for example, files that they store, or printing, or something like that, and clients, which are like your personal computers connected into the network that are accessing the servers to request their services. So what sort of things would we want to say about such a network? Well, because we don't know the precise finite number of devices that are connected, we might want to talk about an arbitrary device by having a variable that ranges over devices, and we might want to state some simple properties of the connectivity of such devices. For example, we might express, so a basic relation in the network is going to be that one device X is connected to another device Y, and we might want to assert the true in our model property that connectivity relation is symmetric. So we can do that in first order logic by using the ability in first order logic to quantify over variables. So in our case, the variables are ranging over devices. So So for all devices X, for all devices Y, if X is connected to Y, then that's the same thing as saying that Y is connected to X. So that implies Y is connected to X. We only need the implication in one direction because that implies the implication in the other direction. So in order to say this, we've got our variables ranging over devices. We have this connected relation here, and so this is part of the vocabulary for expressing formulas and that is called a predicate or a relation symbol because it expresses a relation, in this case the connectedness relation. And the important characterization of relations or predicates, the relations and predicates means the same thing here, is that what they do is their arguments are elements of the universe of discourse. In our case, the universe of elements of discourse is the collection of devices, and so the arguments here are devices, and the result of testing whether two devices are connected is a truth value. So here we get back into the world of formulas that have truth values, and this formula as a whole also will have a truth value, so that we could take it as an axiom for our notion of connectedness that it should satisfy this symmetry property, as it's called. So we might also have another predicate saying when a device is a server, and another predicate saying when a device is a client. And perhaps in our model we'd like it to be true because it's a server-client model that for all devices, then that should be server for all devices X. X is either a server or it's a client. And depending exactly on how we want to model things, we might also have a property saying that a device is either a server or a client. And if you had a device that's in practice fulfilling both roles, you would divide it into two parts, one which is the server part and one which is the client part. So one might have models that work in different ways. For the sake of illustration, we shall assume that property here. So just to show we can write it down. So for all X, it's not true that X is a server and X is a client. And we might have some specific kinds of servers, for example, so printers. So for all X, if X is a printer, then X is a server. I don't want to give a complete set of axioms here because that would be a bit tedious. I just want to give you examples of the kind of formulas we have in predicate logic, and the formulas here are, as in propositional logic, are stating propositions. So in the end we're stating a property that's either true or false, and the role of these formulas is kind of to act as axioms, that they're axioms saying that in any of the client-server models that we have in mind, then these properties should hold. One might also have something like file server here and so on. Let me just put some dots down here to say one might extend this model. Okay, so that's an example of a situation in which we're using predicate logic because we've got predicates, we've got variables, where the variables range over objects in our universe of discourse. So in this case, as I said, devices. The predicates are relations between devices, or in the case that they just have one argument, properties of devices. And importantly, we're allowed to universally quantify. We can also existentially quantify over the universe of discourse. So here we're quantifying over devices. Okay, so I'll just give one more example. So let's take an example from mathematics now. So in mathematics, let's see, a natural language to consider is the language of a ring with order. So a ring has addition and multiplication, basically, but addition forms a group. So you also have subtraction, and you have 0 and 1, which are respectively the units of addition and multiplication. And with order, well, we have well-known rings with order, like the integers and the rationals and the real numbers. So here are some properties we might want to state about in the language of rings with order. So for example, all x, if x is greater than or equal to 0, then there exists a y such that x equals y times y. Maybe in such cases one would put some brackets in sometimes. You don't always need to make it clear what's being stated. Okay, so here we're using the order relation, the equality relation. So the order relation is, again, a predicate symbol. It takes elements from our universe, which in this case are numbers. We haven't said what kind of number for the moment, but we can still make the formula without saying what kind of number. And we have an order relation, we have the equality relation, and we also now have a different kind of thing, which is multiplication here. This is not a predicate because it takes two numbers as its arguments, but it doesn't return a truth value, it returns another number back. So this is called a function symbol as opposed to a predicate symbol. And of course, if we read this in the natural way, it's saying that every non-negative number is a square number. So this is clearly going to be false if we interpret it in the ring of integers and also in the ring of rationals, a famous argument from the ancient Greeks that 2 has no rational square root, but it's going to be true in the real numbers. And for example, a formula that would distinguish between the rationals and the integers is the formula that states that every non-zero number has a multiplicative inverse. So let's formulate that one. So that would be for all x, if x is not equal to 0. So if we were writing that in the long-winded way, it would be like this. But normally we would say instead, let me just put it down here, we would just write it that by the natural shorthand, x not equal to 0. Anyway, we'll resume the formula up here. So for all x, if x is not equal to 0, then there exists a y such that x times y equals 1. So this is false in the integers, and true in the rationals and the real numbers, because they're both fields, whereas the integers are just a ring. And I could consider many more complicated formulas than this, but I think the examples we've done are enough to continue with the lecture now. And what I want to do is to move from the specific examples we've considered, so the language for the network of devices and the language for ordered rings, which we've been using, which we've been interpreting over different structures, as they're called, the integers, the rationals, and the real numbers. And I want to now go from that to the general language of predicate logic. So these will all be examples of, these will be specific instances of the general language of predicate logic. So to begin with, what the language is going to tell us, what the formulas are that we have. And in order to decide, in order to know which formulas we have, we need to be given some data, which is the basic vocabulary that we use to build the formulas. And that basic data consists of the function symbols and the predicate symbols that we have available. So we have what's called a signature. So a signature is going to be a pair consisting of two collections of data. So the first one is the set curly f of function symbols, and the second one is the set curly p of predicate symbols. So this is set of function symbols and this is the set of predicate symbols. So let's write that down in a bit more detail. So F is a set of things called function symbols. So a function symbol is basically given by its name, but it also has another associated piece of information. So let's use like a little f to talk about a generic name for a function symbol. But it doesn't just have a name, it also has some other piece of information which is called its arity, which is the number of arguments it takes. So when you apply the function symbol, how many arguments does it have? So each with an associated arity the arity of f. So that means the arity of f, and that's a number, and I like to allow it to also be 0. So 0 is a function symbol that takes no arguments, and that's a special case. So in the case that the arity of f is 0, then we call f constant, or a constant symbol. So in our examples, well, there weren't any function symbols, or we did not use any in the example of the network of devices. But in the mathematical example of ordered rings, we did use function symbols. So in second example, so the first one was the network of devices. So in the second example, function symbols, the function symbols were well, multiplication, which is arity 2, addition, although we didn't use it in our formulas, but it's there because it's an operation on rings, which is of arity 2. You might also have negation, either of arity 2 or arity 1. Let's ignore that for now. It doesn't really matter which one you include. And actually in first order logic you don't even really need to include it at all, because first order logic is rich enough that just using plus you can express properties of negation. That's an exercise if you want to think about it. But we did have two important constant symbols which we did use. So we had 0 and 1. So those were both constants. So those are function symbols of arity 0. Let's see if I can scroll. Oh, I can like this. This gives us a bit more space to talk about the predicate symbols. So P, curly P, is a set of predicate symbols and again, so I'll use just P, not a curly one this time, as a generic name for a predicate symbol. And this also has, again, each with associated arity of P is greater than or equal to 0. Some authors restrict the arities of predicate symbols to be greater than or equal to 1, but it is useful to have the arity 0 ones, and a predicate of arity 0 is called a propositional constant. And in predicate logic, the propositional constants are basically just the same things as propositional atoms from propositional logic. So we had plenty of predicate symbols in the two examples we looked at. So in the first example, the predicate symbols were well, let me just check. Let's go back. Let's go back and have a look. So connected was a predicate symbol of arity 2. It's taking two arguments. Server, client, and printer were all predicate symbols of arity 1. So let's go back to the page we were working on here. So they were connected with arity 2. Let me just write that like that. And server, client, printer of arity 1. And in the second example, we had the order relation, so less than equals, so that's again a relation of arity 2. And also equality is like a predicate symbol. It takes two arguments, both from the universe of discourse, so in this case 2 numbers. We would also have it in the server client example. We could take it when 2 devices, talk about when 2 devices are the same, and again this has arity 2, but I'm going to put brackets around this because at least the way I'm going to do things, we're not going to include equality in the signature because we're always going to have equality available. So we don't include in signature. So it is a logical symbol. It is a predicate symbol of arity 2, but it's a logical symbol. It's part of logic. It will always be available to us. So the point of the signature is to specify the particular predicates and function symbols that we have that are not predicates and function symbols that make sense whenever you're using logic, but they are the particular ones intended to describe the situations that we want to talk about. So in the first example, devices, and in the second example, properties of numbers. So we don't include in signature because equality is a logical symbol. At least that's the way we're treating it. Okay, so once we've got the signature, then we can build, once we've got the signature, we can build formulas according to some very clear rules for how we build formulas. But in order to build formulas, we first need to build something else, and those are called terms. So whereas formulas are ultimately going to express truth values, so they're going to express propositions, that's statements that have a truth value, terms are going to be compound expressions, that's complex expressions that stand for, that is denote is another way of saying that, so complex expressions that denote elements of the universe of discourse. So for example, if we go back to the numbers x times y and y times y, that's a complex expression. It's not just a variable, it's built up by applying an operation to variables. It is not a formula because it actually stands for an element of the universe of discourse, in this case a number. Also 0 and 1 are also, they're not variables, but they also stand for numbers. They're not propositions, so they don't count as formulas. So our rules for terms, what we're going to do next. So terms are built up by the following rules. So let me just say, so these denote, that means they represent or stand for, they denote elements of the universe of things we're talking about, the universe of discourse, or let me just say elements of the universe that we're talking about. So as I keep on saying, in the first example that would be devices, it would denote devices, and in the second example they would denote numbers. So these are built according to the following rules. So any variable x is a term, and in general we give ourselves an unlimited supply of variable names to use. And secondly, the only other way we have of building terms is that we can build them inductively in the following way. Once we've built smaller terms, we can create a larger term. So if f is a function symbol, so by that we mean f belongs to the set of function symbols in the signature, declared in the signature, and if f has if the arity of f is n, and if we have n terms already constructed that we can give as arguments to f, so and t1 through to tn are terms, so if we've already built n terms, so again these could be variables, or they could be terms that we've built by applying this rule that we're now explaining, that I'm now explaining. So then we get a new term by applying the function symbol to the n different argument terms. Terms too. Sorry, this isn't R terms, this is a term, f applied to t1 to tn. I should correct that. So in particular, in the case that f is a constant symbol, it expects no arguments, so we vacuously don't need to supply terms t1 through to tn because n is 0. So then just, well, if you were very strict about it, you might say it should be f open brackets, close brackets, but of course we won't write that. Then we'll just say that in that case f itself is a term, just like 0 was a term and 1 was a term. We used those, and also we're not going to be too fussy about how we write terms. So when we've got, for example, the multiplication symbol, function symbol from the example of a ring, then, so strictly speaking, we would, by the above rule, we would write this for the multiplication of x and y, but nobody ever writes that in practice, so we'll allow ourselves to often use convenient notation for binary operations and write them infixed like this. So this is a term according to the above rules because x is a term, y is a term, and then this is the term that's built from x and y as t1 and t2 by applying the multiplication symbol to it. And also 0 is a term. So this is in the second example. So that's right. Okay, so those are terms, and we use, so we typically, so let's put this at the bottom, typically use T, S, and U to range over terms. So we'll write want to say something holds for any term t, such as this is a specific term x dot y, but if we want just a generic way of referring to a given term, then we'll use a letter like t, s, or u for it. These things are called meta variables. They're not variables in the logic itself, but they're like symbols we use to vary over terms. Okay, so those are terms. Formulas can be built. Now that we've got the rules for terms, we can say what a formula is. That's a bit more complicated, so we need a fresh sheet for it. So what are the rules for building formulas? So a lot of them mimic the rules for formulas in propositional logic. Sorry, this word's a little bit messy here, but I think you can read it. So in particular, we're going to have, let me just put these at the top, even though it's not really the starting point. So we're going to again use the Greek letters phi and psi to stand for formulas, and we're still going to have that true and falsum are formulas, as in propositional logic. We're going to also have that if that we can build new formulas from formulas we've already constructed by using the propositional connectives that we have in propositional logic, so conjunction, disjunction, implication, negation. So if phi and psi are formulas that we've already constructed, then so are all the following. So not phi, phi and psi is a formula, phi or psi is a formula, and phi implies psi is the formula. Okay, so we can build formulas in the same way as propositional logic. Also in propositional logic, we allowed ourselves to include propositional atoms as formulas. So again, in predicate logic, propositional constants, as we're now calling them, will be formulas. But that is just an instance of the more general rule for building what are called atomic formulas, which are formulas that are used as the basis for constructing more complex formulas. So they don't contain any logical connectives in them, but they still, in predicate logic, have a bit more structure to them. In propositional logic, the only atomic formulas, as it were the propositional atoms. But now we're going to have more complicated atomic formulas that make use of the predicate symbols we've got. So to do that, to build the general rule for building an atomic formula is if P is a predicate symbol, declared in the signature. So P belongs to the set of predicate symbols curly p, with whose arity is n. Then, if we're given n terms, we can apply p to those n terms to get an atomic formula. So the idea is we're saying that P holds, the relation P holds of the n terms we've got. So we need n terms, so T1 through to Tn are terms. Then P of T1 Tn is a formula. So in the case that P is a propositional constant, once again then it has arity 0, so we don't need any terms T1 to Tn, and again we just include P itself as a formula. We could write P open brackets, close brackets, but we don't, we just write P as the formula. We actually have one other way of building atomic formulas, which is we have, as I said, equality is like a binary predicate symbol, but it's not specified in the signature because it's a logical symbol. It's always available in any situation that we're using predicate logic. We can always talk about what it means for two elements of the universe to be equal. So we have the same rule for equality, which is that it's always got arity 2, it's not declared in the signature, so we just need to say whenever we've got two terms, so if T1 and T2 are terms, let me scroll down a bit to give a bit more space, if T1, T2 are terms, then there's a formula, T1 equals T2, expressing that T1 and T2 denote, that is, represent equal elements of the universe. And finally, the one missing ingredient is the other formulas built using quantifiers, and the rules for those are very easy. So that's just whenever we have a formula and a variable, we can stick a quantifier in front of the formula. So if phi, a quantifier over that variable, so if phi is a formula and x a variable, then for all x phi and exists x phi are formulas. That's it. Those are all the rules for building formulas. Let me just say one other thing, which is I already talked here about the formula that's built from a predicate symbol as being an atomic formula. Because equality is like a predicate symbol, that also counts as an atomic formula. It's a formula that doesn't contain any smaller formulas inside it. So let me just put a line down here to say these two are atomic formulas. So that is P of T1 through to Tn and T1 equals T2. Those are atomic formulas. Let's just go back to our example here with the formulas talking about the ordered ring structure of the numbers. And so Here we see, let's do this one. Here we've got an atomic formula here with an equality. We're then building a larger formula around it by putting the existential quantification in front. Here we've got an atomic formula using one of the predicate symbols in our signature, in fact the only one in this particular signature, which is the order relation. So again, this is again an atomic formula. So we've got a formula here and a formula on the right of the implication here. So then we're combining these two formulas with an implication, and then we're then sticking another universal quantification on the front, and that universal quantification gives us the whole thing is a formula. So that's how this formula is built up by successive applications of those basic rules for building formulas. Okay, so let's now consider this formula at the top here and consider it in its interpretation in the rational numbers. Now it's false in the rational numbers and it has a determined truth value. So we are interpreting it in the rational numbers, and it is a priori, even before we know that it's false in the rational numbers. That requires quite a proof, but even before we know it's false, we know it has a predetermined truth value. It will either be true or false. Then Euclid, of course, showed us, or at least it's in his Elements, his book of Elements, that there's the old proof from the ancient Greeks that 2 is not a square number. Sorry, it's not the square of a rational number. So that tells us this is false in the rational. So actually nowadays we know. So now, of course, we know that this number is false. But the point I'm trying to make, which maybe I shall make more clearly as follows, is that if we remove this quantifier here, and we're interpreting it in the rational numbers, then we can no longer say whether the formula is true or false or not, because this is the formula x is greater than or equal to 0 implies there exists a y such that x is the square of y. So that will be true vacuously for any negative x, because that will be an implication from a false assumption. But for a positive x, it will be true in the case that x is a rational number that has a rational square root. So that will be true, for example, for 1/4, which is whose square root is 1/2, but it won't be true for x equals 1/4, and this formula is true. It does have a rational square root. This x is greater than or equal to 0 is true, and then this needs to be true too, because the left-hand side is true, and there exists a y that is the square root of y, a rational number y, because we're looking in the rationals, that's the square root of y. So that's false if x is 2, but true, for example, if x is 1/4. So the point is, this formula depends on what element of the universe, remember our universe here is rational numbers, it depends on which element of the universe we are taking x to stand for. But if we put the quantifier back in front, then the formula is either true or false, because we just need to check it for, well, there are infinitely many of them, but nonetheless we're saying that this would be true for all infinitely many different rational numbers x. In fact, it's not true for all of them, so it's false. But the point is, once the quantifier is here, then it is clear that this formula will have a definite truth value when we interpret it in a given structure. Whereas when the quantifier is not here, then the truth value depends on the value of x. And there's really just a very simple way of telling when a formula is guaranteed to have a definite truth value in a given structure or not. And that is, it's guaranteed to have it when all variables are quantified over the universe. So what was wrong when we did not have this quantifier here was that we were just talking about one given value of x. When we put the quantifier on, then we're looking at the formula for all values of x, and then it has a determined truth value. So it's going to be very important to look at when a formula has the property that all its variables are quantified, and such formulas are called sentences. So let's make the definitions that we need to talk about sentences. Let's go to a fresh sheet of paper. So an occurrence of a variable in a formula is said to be bound if it is within, let's write it like that, within the scope of a quantifier either for all x or exists x, quantifying over that variable. So let's write out the formula we were talking about before. Let me just let's just remind ourselves what it was. Let me just go back to there. So I'm going to miss out the quantifier, the for all x quantifier here, and write the formula back. So we're going to have x is greater than or equal to 0 implies there exists a y such that x is y squared. And so what a formula occurrence is, a variable occurrence is it's a single place where the variable occurs. So this is an occurrence of the variable y, this is an occurrence of the variable y, and this is a different occurrence of the variable y, this is an occurrence of the variable x, and this is a different occurrence of the variable x. And here we see that these occurrences of y are bound because these y's appear within the scope of an existential quantifier that's quantifying over y. So these variables y are existentially quantified over. If they were universally quantified over, they would also be bound. But x is not, neither of the occurrences of x are bound because for both of them there is no quantifier over x that quantifies them. So if a variable is not bound, if a variable occurrence is not bound, it's called free. So let's point to those variable occurrences. So these occurrences are free. But if we put the for all x on the front, then all the variable occurrences would be bound. So let me just say, let's just continue the definition here. So it's within the scope of a quantifier. So let's just continue that. The variable occurrence is said to be free if it is not bound. Sorry, if it's not bond, should be bound. And a formula is called a sentence if none of its variables occur free. So sentence if no variable occurs free. So the formula above this is not a sentence. But if we put for all x in front of it, I won't bother copying it all, this is a sentence. Because now if we put for all x in front, then the occurrences of x are now bound. So this is a sentence. And sentences are important because their truth values do not depend on what interpretation we assign to the variable. So only free variables, only when you've got free occurrences of variables is the interpretation of those variables important. If you've got universally or existentially quantified variables, then we're not talking about a particular interpretation of them, but we're quantifying over all possible interpretations of the variables. Okay. Right. So maybe this is a good place to pause this video and to take a break, and then we'll carry on with the second half in another video. Okay, so let me go to the stop button.